Okay, now we're recording. Fantastic. So welcome back, everyone. It's a great pleasure to introduce our third and final speaker for the day, who's Alex Iosevich, who's going to talk about signal recovery, restriction, and the uncertainty principle. And I'm trying to convince Alex to come and visit us in St Andrews, but I guess this has to do for the time being. So over to you, Alex.
Thank you very much. It's an honor and a pleasure to be here, and I'm definitely going to visit you guys in Scotland. This is an absolute must. I love Scotland, and this will be a great opportunity. So I would like to talk about signal recovery restriction and the uncertainty principle. And what I've done for this talk is I really pared it down to the bare bones to get across main ideas. Also, please interrupt me anytime for any reason. If I cover a bit less than I planned, the world is not going to end, at least not for that reason. Okay, so there we go. So let me begin with the classical restriction conjecture. So this is the sort of the bread and butter of harmonic analysis. So it says that if you take a function, take a Fourier transform, restrict it to the sphere, then the resulting operator satisfies the LP-LR bound in a certain range. One can talk for days on end on why this result is important. It has implications in geometric measure theory. It has implications in PDE. It truly is one of the central problems in mathematics. The reason I wanted to start out with the restriction conjecture is because I wanted to give you the motivation for the signal recovery results that follow. Okay. So first, let me mention for those who don't work in that area that the conjecture was solved in 2 dimensions. It was solved independently by Charles Pfefferman and Anthony Sigmund. In higher dimensions, the problem is wide open, even though there have been some brilliant results by people like Bourgain Guth, Ustein, Tau, Thomas Wang, and others. Okay, so let me give you a signal recovery perspective on the restriction conjecture. Okay. By the way, can you see the screen? Everything is good? Awesome. So suppose you have a compact set of positive Lebesgue measure, and the Fourier transform is known except for the delta neighborhood of the sphere. Okay. And can we recover the indicator function exactly? Okay. So we take the indicator function, we write it as the inverse Fourier transform of the Fourier transform, and we split up the integral over the known frequencies outside of the delta neighborhood of the sphere, plus the unknown frequencies. Since the unknown frequencies are unknown, the best we can do is estimate them out and hope for the best. So what happens if we do that? If we do that, we just apply Holder's inequality and bound the second term by the volume of the annulus times essentially the LR norm of the restriction operator. Why do I say essentially? That's because for small delta, this is, so in the limit, this is the LR norm of the restriction operator. So for small delta, you'll get the same bounds by standard analytic tricks. Okay. Then if you assume the restriction conjecture, this is bounded by the volume of S delta times the LP norm of the function, which in this case is just a measure of a to the power of 1 over p. Okay? And now suppose that a miracle happens. By a miracle, I mean assumption, that the right-hand side is less than a half. Okay? Which happens up to constants if the measure of a is bounded by delta to the minus p. Okay? Then all we do is we go back over here. We ignore the second term. We take the first term, compute its modulus, and round it up to 1 or down to 0. Since the second term is less than a half, and since the indicator function takes values only 1 or 0, we win. Okay? And here is the point. We can easily obtain this result by any number of methods if p is equal to 1. That's more or less the classical Fourier uncertainty principle. But the restriction conjecture affords us a larger value of p, hence a less restrictive recovery condition. And largely the theme of this talk is in the presence of a non-trivial restriction estimate, one obtains a better recovery condition for a signal recovery problem. Now, let me be clear. the signal recovery problem in a continuous setting, as I described it, is thoroughly impractical. This is not what the talk is really about. But this is the motivation behind the classical signal recovery problem that I'm going to talk about. Are there any questions at this point? Is the setup clear? Okay. And okay. So what happens in the practical setting, the finite setting? So we take a signal of length, of finite length, say length capital N, say multidimensional signal, and which is just a function from Z and D to complex numbers. And suppose that the Fourier transform defined with this normalization is transmitted. If the whole Fourier transform gets through, then we can recover the function by Fourier inversion, right? So in other words, if our coding scheme is the Fourier transform, and if there is no interference, we can get the function back by performing Fourier inversion, okay? But the question in signal recovery, one of the basic questions, is what happens if some of the frequencies are lost? This can happen due to a variety of factors, noise, interference, security, whatever. And the question is, under what assumptions can we recover the original function exactly and uniquely? It turns out that we can do that if the function is supported in the set E, and the size of E times the size of the missing frequencies is less than n to the d over 2. And the main tool is the Fourier uncertainty principle. Okay. All right. So the classical uncertainty principle, which can be proved in two lines using Fourier inversion and the triangle inequality, is the following. So if H is a signal from Z and D to C, then the support of the signal times the support of the Fourier transform of the signal is bigger than or equal to n to the d. Okay? And what I'm describing now is a method due to Matolchi, Jukes, and Donahoe and Stark. So quite often, most papers credit Donahoe and Stark, who wrote a brilliant paper in 1989 on this topic. But it turns out that in 1973, Matolchi and Jukes wrote a paper in French. And since in the US we don't like foreign languages, this flew under the radar. But at least the method I'm describing is already contained in Matolchi-Jukes' paper. Okay. All right. So suppose that a function supported in E with frequencies in S unobserved. Okay. So what does it mean that F cannot be recovered uniquely? It means that there is a signal G, which has the same size of the support. We don't even need to know what the support is. And the Fourier transform of F and the Fourier transform of G agree away from S. And F is not identically equal to G. So this is what it would mean that we cannot recover the function exactly, signal exactly. Okay, so what do? We subtract G from F. Then the Fourier transform has at most the size of S non-zero entries by construction, since F and G agree away from S. And the support of H has size at most twice the size of the support of F. So we apply the uncertainty principle, which tells us that the size of the support of F times the size of the set of missing frequencies is bigger than or equal to n to the d over 2. So if we assume the opposite, we get a contradiction, and H is 0, and the recovery is unique. Okay. Now, in the finite setting, there's any number of ways to actually implement this recovery, for example, by least squares method, etc. This is a slightly different topic that I'm going to touch upon later in this talk. Okay. Is the method clear? It shows that that whenever you have an uncertainty type principle, you can reverse it and come up with an exact recovery condition. Okay. In some sense, in the language of analysis, this is an inverse problem of sorts. Okay. All right. Now, the classical uncertainty principle is in general sharp. There are many examples. Well, There are many examples. Many in the sense that you can't count it on your fingers, but in reality, there are very few. I'm going to make this precise. So suppose n is an odd prime and S is a k-dimensional subspace. Then the Fourier transform up to a normalizing factor is just the indicator of the orthogonal subspace. Okay? And since the size of the space times the size of the orthogonal space is n to the d, this shows that the classical uncertainty principle is sharp. Okay? If n is not prime, you can take any subgroup, compute the Fourier transform, and play the same game. Okay? But what is interesting is that in a typical case, we can do much better. In other words, it is well known what the sharp examples are for the uncertainty principle. They're all subgroups. What is less clear is when do you have near sharpness? What are the near extremizers for the uncertainty principle? And as you'll see, this point is going to be addressed, albeit in an indirect way. Okay. Quick question about time. Do I have until 11:20 or 11:30?
We're reasonably flexible. I'll probably stop you at 16:32 or something like that. But you know, you can use the full half hour.
No, I'm not gonna go over a half hour for sure. Probably less. I just want to make sure. Thank you. Okay. So so the main tool that's going to prove the result that I want to discuss today is Bourgain's lambda Q theorem. So Bourgain's theorems, this is probably my favorite. So he proved that if G is a locally compact abelian group and you choose any collection of n orthogonal functions with L infinity norm bounded above, let's say by 1, and then if you choose a generic subset of integers 1 through n, by generic, I mean you just choose them randomly with equal probability. And you choose it of size n to the 2 over q, then the LQ norm of the trigonometric series with phi i's from this random collection is bounded by a constant that depends only on q times the L2 norm, which is just sum of the coefficients squared. Okay, this is an absolutely amazing result because of its generality and applicability. Also, those of you who are used to these types of things recognize this as an extension theorem. Okay, it's a kind of a dual to the restriction theorem. Okay. One interesting thing about this result is that it has a very simple built-in uncertainty principle. And this uncertainty principle leads to a much improved recovery condition for generic sets of lost frequencies. Okay. All right. So one consequence of Bourgain's lambda Q theorem is the following. It's basically a restatement in the setting of Z and D. So if you have a signal from Z and D to complex numbers, and the Fourier transform is supported in S, then for a generic set of size n to the 2d over q, generic in the same sense, means you choose it randomly and with extremely high probability. When I say extremely high, it's 1 minus exponential tails. Okay? Then the normalized LQ norm of the function is bounded by a constant that is independent of capital N times the normalized L2 norm of the function. Okay, this is just a restatement of Bourgain's theorem in Z and D, where for our collection of orthogonal functions, we take all the characters. Okay? And as I said, this is going to lead to a dramatic improvement of Donoho, Stark, Matolchi, Jukes for exact recovery. Let me also mention one more thing. There have been a number of results in literature, for example, by Candice, Roberg, and Tao, and others, getting improved conditions for random sets. The point of this line of inquiry is that it unifies the results for random sets and deterministic sets. For example, this results holds if S is random, but this results also holds for certain deterministic sets like paraboloids and spheres. All right, so this is a joint work with Zita Mayeli from earlier this year. So if F is a signal on Z and D supported in E, suppose that the frequencies in S are unobserved, okay? And here we are just going to assume that this estimate that I just mentioned holds whenever G hat is supported in S for some Q bigger than 2. Okay, so we have already seen that this estimate holds for a generic set of size approximately n to the 2d over q. But the assumption of this theorem is just that this restriction type estimate holds. Then F can be recovered exactly and uniquely, provided that the size of E is less than n to the d divided by a constant that depends only on q and on the constant in the restriction inequality. Okay, and please note how much stronger this is than the classical statement, right? The classical statement would be that the size of E times the size of S is less than n to the d over 2. Here, we are only requiring that the size of E is less than just a fixed constant times n to the d. Okay? All right. So, okay. So let's go ahead and prove this. The proof is very simple. The idea here is to notice that Bourgain's result is applicable. Once you do, the proof essentially writes itself. So suppose that S is generic, as in Bourgain's theorem, although we don't need to assume that it's generic. We just need to assume that Bourgain's theorem, the conclusion of Bourgain's theorem holds. Okay? So suppose that F is supported in E and F hat is supported in S. Then we rewrite Bourgain's theorem as follows. So instead of normalizing by n to the d, we take it out, we divide by the size of E, and we multiply on the outside by the size of E to the 1 over Q. So this is just high school algebra applied to the left-hand side of the restriction inequality. On the right-hand side, by assumption, we have a constant, and here we renormalize the L2 statement. Namely, we take out n to the minus d over 2. Then we take out the size of E to the 1/2. And now we have an average with respect to x and E, exploiting the assumption that F is supported in E. Okay? And here we simply do the arithmetic. So we take size of E to the 1/2 minus 1 over Q to one side. We take capital N to the d over 2 minus d over q to the other side. The LQ and the L2 terms disappear by Holder's inequality. And then we take roots, and we see that the size of E must be larger than n to the d, divided by the restriction constant, divided by 1 over 1/2 minus 1 over q. Okay? And the conclusion then follows by the exact same method that we described before. Namely, suppose you send the signal F, where frequencies in S are lost. What does it mean that we cannot recover them? It means that the Fourier transform of F and G agree away from S, right? So we take F minus G. We notice that the Fourier transform is supported in S, and we notice that the support of F minus G is at most twice the support of S, and then we apply this uncertainty principle, and we recover a stronger recovery condition. Okay? So, but here's a question. How does one actually recover the signal? Sorry. As I mentioned, I edited a couple of slides an hour before the talk, and this is where spelling errors come from. So how does one actually recover the signal? Okay? And there is an absolutely beautiful result by Kashin and Timlikov. And variants of this result have existed before, but their form is particularly satisfying. Okay? What they showed or more precisely, if you take their result and you plug it into this context, here's what you get. That under the assumption of the theorem we just proved, the signal can be recovered as follows. You take all the possible functions g, so that the Fourier transform of g is equal to the Fourier transform of f. And among all those functions, we find the one with the smallest possible L1 norm. So it's the argmin. Okay? And that is the exact. And if we know in advance that the conditions are satisfied, namely that the exact and unique recovery is possible, then this minimization process is going to yield the correct, is going to yield the original signal. Okay. And it just so happens that yesterday I played around with this because there's the original sort of recovery mechanism described in a Donahoe-Stark paper involving the method of least squares, and it basically cannot be implemented. It runs super exponentially. But yesterday I wrote Python code that very, very quickly recovers signals of length, say 1,000, even in my laptop. Okay, and I prepared another topic, but I don't think I will have time to go over it. So I think that I'll stop here.